Dear students, welcome to session 1 on the topic of radioactivity, chapter 12 in your book between the pages 283 and 307. Before we move on to the presentation, let me brief you on the three important discoveries at the end of 19th century that revolutionized the world of science. They are the discovery of X-ray by Wilhelm Röntgen in 1895, followed by the discovery of radioactivity by Henry Becquerel in 1896, and the discovery of electrons by J.J. Thomson in 1897. Out of these, we shall focus on radioactivity and the basic concepts associated with it. As usual, I have split the chapter to be discussed into two sessions. In the first session, we shall see the structure of an atom, the structure of the nucleus, what is atomic number and mass number, what are isotopes, isobars, and isotones, basic concepts of radioactivity, and the properties of the three types of radiation, alpha, beta, and gamma. The discovery of electrons by J.J. Thomson and the alpha scattering experiments of Rutherford led to the following structure of an atom and nucleus. All matters are made up of tiny particles called atoms, and each atom has a very small and a very dense core inside it called the nucleus. Now let's peep into the atomic world. An atom consists of electrons, protons, and neutrons. The protons and neutrons reside inside the nucleus of the atom, which is at its center and are called nucleons, while the electrons revolve around the nucleus in specific orbits called stationary shells. In each stationary shell, the electron has a definite energy. The maximum number of electrons in a shell can be determined by the expression 2n square, where n is the shell number. The various shells around the nucleus for n is equal to 1, 2, 3 and 4 etc. are named as k, l, m, n and so on, and these shells can accommodate at the most 2, 8, 18, 32 electrons respectively, satisfying the expression 2n square. Now, a proton has a positive charge and the electron has a negative charge. A neutron is an uncharged particle about the same mass of proton. The mass of an electron is approximately 1 by 1840 times the mass of a proton. Now, having known about the atomic structure, let's move on to know about the nuclear structure. The nucleus is at the center of atom, whose size is about 1 lakh to 10,000 times smaller than the size of an atom. It consists of nucleons, that is protons and neutrons. Proton has a positive charge, which is 1.6 into 10 power minus 19 coulomb. Here, plus E signifies its charge is same as that of an electron but positive, and its mass nearly equal to 1.67 into 10 power minus 27 kilogram. The neutron is an electrically neutral particle, that is charge is zero, and its mass is almost nearly the mass of proton. Hence, the nucleus is positively charged. Now, having known about nucleus, let's see some more concepts related to it. The total number of protons in the nucleus determines the place of the atom in the periodic table and is called the atomic number of an element, denoted by the symbol capital Z. The total number of nucleons, that is the number of protons and neutrons inside the nucleus, define the mass number of an element, denoted by the symbol A. Remember, students, that the number of electrons is always equal to the number of protons in an atom. Also, in order to find out the number of neutrons present, it is determined by subtracting the atomic number Z from the mass number A, that is A minus Z. Since the mass of an electron is negligible as compared to that of proton, now recollect what I said about the mass of electron. It is 1 by 1840 times the mass of proton. Hence, the total mass of an atom can be considered to be same as the mass of its nucleus. Students, go through the models of hydrogen, helium, and sodium atoms in page 284, along with a note given to understand the difference between a chemical change and a nuclear change. Now let's understand the nuclide notation. You see how the representation of an element along with its mass number capital A and atomic number Z to be written. X is the chemical symbol of any element. The mass number A should always be written as a superscript and the atomic number Z as subscript. Now, what are all the information you gather in a nuclide notation? When you see an element, look for the subscript as it denotes the number of protons, which also indirectly tells us that it is the same as the number of electrons. Next, look at the superscript. It will give you the total number of protons and neutrons present in the nucleus of the atom of that particular element. Now, when you subtract the values from superscript A, the value of subscript Z, you will get the number of neutrons present. In the example of C12-6, chemical symbol of carbon is capital C. First, you need to see the subscript. It's 6. Hence, number of protons, which is equal to number of electrons, is 6. Now look at the superscript A. It denotes 12. Hence, number of protons and neutrons together is equal to 12. Hence, if you want to know the number of neutrons present, then it is A minus Z, that is 12 minus 6, which is equal to 6 neutrons. Now let's move on to the next subtopic to understand about isotopes, isobars, and isotones. Now what are isotopes? The atoms of same element, I repeat, the atoms of same element having same atomic number Z but different mass number A are called isotopes. In other words, the atoms of isotopes have the same number of protons but different number of neutrons in their nucleus. Obviously, the isotopes have the same place in the periodic table as it depends on the atomic number Z. See the examples of hydrogen. It has 3 isotopes: protium, deuterium, and tritium. Each isotope has the atomic number Z as same as 1, but the difference lies in the mass number A. Students, check with the examples given of carbon and chlorine. For your kind information, tin has the largest number of isotopes, that is 10. Isotopes are of two types: stable isotopes and unstable or radioactive isotopes. In stable isotopes, as the name suggests, are isotopes which have the number of neutrons nearly equal to the number of protons in their nucleus. If you see the examples of chlorine isotopes, each isotope in its nucleus has 17 protons. The isotope chlorine 3517 has 18 neutrons and isotope chlorine 3717 has 20 neutrons. In the case of unstable isotopes, they have the number of neutrons much more than the number of protons in the nucleus. In uranium 235-92 and uranium 238-92, each isotope has 92 protons, but uranium 235-92 has 143 neutrons, while uranium 238-92 has 146 neutrons inside the nucleus. In both cases, the number of neutrons are far more than the number of protons. Hence, they undergo radioactive decay, which finds great medical use. Now coming to isobars, the atoms of different elements, I repeat, the atoms of different elements which have the same mass number but different atomic number are called isobars. In the given examples, you see sodium and magnesium have same mass number, that is 23, but different atomic number, that is 11 and 12 respectively. Hence they are isobars. Similar is the case of carbon and nitrogen. Now question to ponder. Find out from the book in page 286 what are mirror isobars. Now, what are isotones? The atoms having different number of protons but same number of neutrons, that is different mass number A and atomic number Z, but same A minus Z are called isotones. Like in the given examples, sodium 2311 and magnesium 2412, potassium 3919 and calcium 4020, their mass numbers and atomic numbers are different, but the number of neutrons in each pair is same, that is 12 and 20 respectively. Now students, after studying in depth the atomic and nuclear structure, now let's move on to radioactivity. Henry Becquerel discovered the phenomenon of radioactivity in 1896. Radioactivity is the spontaneous emission of alpha, beta, and gamma radiation by the nuclei of heavier atoms. When I say heavier atoms, isotopes of nearly all elements whose atomic number is greater than 82 are radioactive. Most commonly known radioactive substances are uranium, radium, polonium, thorium, and so on. Radioactivity is a spontaneous process. No physical change, such as change in pressure and temperature, or chemical change, such as chemical treatment or oxidation, doesn't change the nature of radiation emitted and its rate of decay. Radioactivity being a nuclear phenomena, it is also a random phenomenon. From the radioactive substance containing a very large number of atoms, there is no way to predict when or which nucleus will decay at any moment. In 1903, Rutherford experimentally studied the nature of radiations emitted by a radioactive substance. These radioactive substances emitted radiations are of three types: positively charged, negatively charged, and uncharged particles, which were named as alpha, beta, and gamma respectively. Students, go through the experimental illustrations given in page number 287. Now let's see the comparison of the properties of alpha, beta, and gamma radiations. By nature, an alpha particle consists of two protons and two neutrons. In other words, it's a helium nucleus. Beta particles by nature are the fast moving electrons emitted from the nucleus of an atom. Students, you might wonder how electrons stay inside the nucleus, but for your information, inside the nucleus, whenever a proton changes into a neutron, a beta particle is emitted. The beta particle don't reside inside the nucleus in the form of electrons. Gamma radiations by nature are electromagnetic waves like X-rays and visible light. The mass of an alpha particle is roughly 4 times the mass of proton and its charge twice the charge of a proton. The mass of a beta particle is that of a mass of an electron and its charge is same as that of an electron, while gamma radiations are uncharged and they don't possess mass. The speed of alpha particle is of the order of 10 to the power 7 meter per second, which is comparatively slow to beta particle, which is 10 to the power 8 meter per second, which is again relatively slower than gamma radiation, which travels at the speed of light, which is 3 into 10 power 8 meter per second, or in other words 3 lakh kilometer per second. The ionizing power of alpha particle is 100 times that of beta particles and 10,000 times that of gamma radiation. Students, you should know ionizing power is the ability to knock off the electrons in an atom and make it an ion by collision. The penetrating power of gamma radiation is very high. It is about 10,000 times that of alpha particle and 100 times that of beta particles. Gamma radiations can easily pass through the human body. Therefore, they cause immense biological change. Out of the three radiations, alpha, beta, and gamma, the gamma radiations are most energetic. Therefore, they have a smaller rate of collision with the atoms or molecules of the medium through which they pass. Thus, they have maximum penetrating power. Gamma radiation can pass through 30 centimeter thick sheet of iron. A thick sheet of lead is required to stop them, whereas an alpha particle can be easily stopped by a thick paper. It requires 5 millimeter thick of aluminum sheet to stop beta particles. Students, that brings us to the end of the session 1 on this chapter of radioactivity. go through the pages between 287 and 290 before we get connected in the second session. Bye till then, take care.